The blister beetle, a thumbnail-sized insect that produces one of the most destructive chemicals in nature. 1 gram kills a horse. Touch it, blisters within hours. Swallow a trace amount, your kidneys start failing from the inside. Roman battlefield surgeons knew this, and for 2,000 years, they used it anyway, on purpose, on dying soldiers. Modern medicine just ran the clinical trials, and it works. The beetle is called Lytta vesicatoria. Most people know it by another name, the Spanish fly. For centuries, that name meant one thing: aphrodisiac, slipped into drinks, blamed for deaths, the kind of substance that shows up in history's darkest chapters, not in a pharmacist's cabinet. But underneath that reputation was a molecule that didn't care about any of that. Cantharidin is what the beetle produces, a terpenoid compound secreted as a defense mechanism. The beetle doesn't sting, it doesn't bite, it simply bleeds this chemical from its leg joints. Whatever touches it pays the price. The mechanism is specific and brutal. Cantharidin blocks protein phosphatase 2A, the enzyme your cells depend on to regulate growth and death. Block it, and your cells lose the ability to stop dividing. In cancerous tissue, that same ability is already broken in the opposite direction. Cells are dividing where they shouldn't be. Cantharidin can force those cells to self-destruct.
That is not what the Romans understood when they were grinding beetles into wound dressings on a battlefield. They understood results. Applied carefully, the blisters it raised on skin could reopen infected wounds that had closed over without a blade, drain the fluid, expose the tissue, treat what was actually killing the soldier. Roman military surgeons were more precise than most people assume. Ancient texts, including Pliny the Elder, recorded cantharidin's use on soldiers with injuries that had no other treatment. Not as a cure, as a last option that sometimes worked. The gap between what they observed and what was actually happening chemically is 2,000 years wide. Science just finished crossing it. But all that is the controlled version. The uncontrolled version is what made this beetle infamous. Ingested, cantharidin doesn't stay where it's put. It passes through the stomach intact, gets filtered by the kidneys, and burns them from the inside on the way out. The result? Hemorrhagic inflammation of the urinary tract, structural damage, and above 10 milligrams, organ failure. 10 milligrams is roughly the amount in a small cluster of dry beetles. You wouldn't know you'd taken too much until it was already too late to stop it. Same compound, same chemistry. The difference between battlefield medicine and fetal poisoning isn't the molecule. It's quantity, delivery, and the knowledge of the person applying it. Roman military physicians understood that distinction in practice 2,000 years before anyone could explain it in a laboratory.
Here's what should have happened. A substance this aggressive, one that blisters skin on contact, destroys kidney tissue in microgram quantities, with a centuries-long record of accidental poisonings, should have been abandoned the moment safer alternatives existed. That's how medicine works. You find something less dangerous, you move on. Cantharidin didn't move on. Researchers kept returning to it, not for wound care, but because in cancer cell lines, it was triggering programmed cell death in liver cancer at concentrations that left healthy tissue largely intact. That selectivity is everything. Most chemotherapy doesn't discriminate. It attacks all fast-dividing cells, healthy and cancerous alike. That's why it causes the damage it causes. Cantharidin was showing targeting that synthetic compounds couldn't replicate. In 2023, the FDA approved a cantharidin-based topical solution, Ycanth, for molluscum contagiosum, a viral skin condition. A beetle defense mechanism, documented in Roman military medicine, refined across 2,000 years of use and misuse, cleared a phase 3 clinical trial. Not as a curiosity, as a drug. The ancient observation wasn't folklore. It was an accurate read on a real biological mechanism, one that science had only just developed the tools to explain. The beetle was right. It just took us 2,000 years to catch up.
The cone snail, a creature so slow it cannot chase you, small enough to fit in a child's palm, so visually unremarkable that beachcombers pick them up by the thousands every year because the shell is beautiful and nothing about the animal inside looks dangerous. Some of those people died within the hour. The cone snail fires a harpoon-like tooth in any direction, including backwards, including through a closed fist. No antivenom exists. There has never been one. Roughly 30% of untreated stings are fatal. The ones that aren't leave the victim fully paralyzed and conscious while the toxin works through their nervous system. You feel everything. You cannot move. You wait. That venom is now sitting in an FDA-approved drug doctors prescribe when morphine has stopped working. The cone snail doesn't produce one toxin. It produces hundreds. Over 700 species distributed across the tropical Indo-Pacific, the Caribbean, and the Mediterranean. Each manufactures its own cocktail of peptide compounds called conotoxins. Small, precisely folded protein chains, each one engineered by evolution to hit one specific molecular target in the nervous system of whatever the snail is trying to kill. Fish hunting species cause instant paralysis. Worm hunters disrupt sensory signaling. The snail doesn't have one weapon. It has a library, refined over 50 to 100 million years.
The compound that became a drug is called omega conotoxin, isolated from a single species, Conus magus, the magician's cone snail, by biochemist Baldomero Oliveira in the 1970s, working at the University of Utah. Oliveira had grown up in the Philippines, watching these animals kill. He wanted to understand the mechanism. What he found was a peptide that blocked one specific calcium channel in nerve cells, the N-type calcium channel, which transmits pain signals up the spinal cord to the brain. Block that channel, the pain signal never arrives. That is not how morphine works. Morphine suppresses the brain's response to a signal that has already arrived. Ziconotide, the drug derived from that snail peptide, intercepts the signal before it travels. Two drugs, entirely different points in the pain pathway. Which means ziconotide works on patients whose nervous systems have built tolerance to opioids. It works when morphine has already stopped working. It works on pain that the entire opioid drug class can no longer touch. A snail perfecting its chemistry for 100 million years solved a problem pharmaceutical research had been circling for decades. But here's the problem. Ziconotide cannot be swallowed, cannot be injected into a vein. The peptide is too fragile to survive digestion, and if injected directly into the bloodstream, it crosses into the brain in concentrations that cause hallucinations, psychosis, and seizures. The compound that blocks pain with extraordinary precision becomes, at the wrong delivery site, something that dismantles the mind.
The only safe administration? A surgically implanted pump placed directly into the fluid surrounding the spinal cord, delivering nanogram quantities of cone snail venom to exactly the points where the pain signal originates. This surgery is not minor. The pump requires maintenance. The dosing window between therapeutic and catastrophic is narrow enough that patients require monitoring for the entire duration of treatment. This drug is reserved for people with no other options. Terminal cancer, end-stage AIDS, chronic pain that has exhausted every other intervention. The patients who receive it aren't choosing it for convenience. They're choosing it because everything else has failed. What remains, after everything else has failed, is venom from a snail with no antidote, delivered in nanogram doses through a titanium pump implanted in the lower back, doing something a century of synthetic pharmaceutical development never managed to replicate. The snail didn't care about any of that. It was just trying to catch fish. Baldomero Oliveira's research should have died in a university lab. The rational institutional response to venom-derived peptides from one of the ocean's most lethal animals, with no clinical precedent and no pharmaceutical interest, was to ignore it. Fund something safer. Work on something with a clearer path to a patent. It didn't die. Oliveira kept isolating peptides. His students kept testing them. Over 2 decades, the lab produced a map of conotoxin activity so detailed it became a fundamental reference tool for neuroscience. Not just pain research, but how ion channels work across the entire nervous system. The snail venom didn't just produce one drug, it produced a toolkit that reshaped how neuroscientists study the brain. Ziconotide was approved by the FDA in 2004 under the name Prialt. It remains the only non-opioid drug in its class. Nothing synthetic has replicated it. Decades of pharmaceutical research into the same target have not produced a compound that does what a snail peptide does naturally. The snail solved it first. We are still trying to catch up. The line between venom and treatment was never a chemical boundary. It was a failure of imagination. The snail was doing pharmacology long before we had a word for it. We just needed someone willing to look at a lethal animal and ask, not how it kills, but how precisely.
The Gila monster, a lizard so slow and so heavy it can barely chase a sleeping animal. No fangs, no venom injection system. It bites down, locks its jaw, and chews, working toxic saliva into the wound through pure mechanical persistence.
Its saliva contains a peptide called exendin-4. A single injection of the synthesized version reduces blood sugar level in type 2 diabetics more effectively than several of the most widely prescribed medications currently on the market. A venomous lizard that chews its victims slowly is now a frontline diabetes treatment taken by millions of people every day. Here's why the lizard has this compound at all. The Gila monster can go months without eating. Its entire endocrine system is built around feast and famine cycles so extreme it developed compounds with no equivalent anywhere else in the animal kingdom. When it eats, it needs to process an enormous caloric load instantly. When it doesn't, it maintains blood sugar stability across weeks of complete fasting with zero external input. To manage that, it produces exendin-4, a peptide that binds to the GLP-1 receptor, the same receptor human insulin response depends on, but it binds with a persistence the human version cannot match. In a healthy human pancreas, a hormone called GLP-1 triggers insulin release when blood sugar rises. It works, but enzymes in the bloodstream destroy it within minutes. The signal is brief by design. Exendin-4 binds to the same receptor and resists those enzymes completely. It stays active for hours. In a type 2 diabetic whose GLP-1 signaling has become sluggish or unresponsive, the lizard peptide does what the human hormone can no longer do reliably. It holds the receptor open long enough for the insulin response to actually work.
Endocrinologist John Eng isolated exendin-4 from Gila monster venom in 1992 at the Veterans Affairs Medical Center in New York. He was not looking for a diabetes drug. He was studying gastrointestinal peptides. He obtained Gila monster venom through a supplier because the lizard's digestive biochemistry was known to be unusual. Unusual turned out to be the understatement of his career. What he found was a compound so structurally similar to human GLP-1, it could slot into the same receptor, but so chemically distinct that the enzymes destroying the human version left it completely alone. Evolution had built a molecule that did a human job better than the human version did it. Not by design, as a side effect of a lizard that needed to survive without eating for half a year. But here's the part nobody talks about. The same peptide that regulates blood sugar with such precision also slows gastric emptying, the rate food moves from stomach to intestine. In the Gila monster, that's a feature. An animal eating one enormous meal every few months needs to extract every available calorie as slowly as possible. In a human patient, that same mechanism causes nausea, sometimes severe nausea, persistent, grinding, weeks of feeling continuously unwell with nothing to do with the drug's therapeutic target and everything to do with the fact that this compound was never designed for a human digestive system. It was designed for a lizard that eats twice a year. The drug works. The side effect is the price of borrowing chemistry from something built completely differently than you are.
Now, here's what should have happened when Eng tried to turn lizard saliva into a diabetes drug. The pharmaceutical industry should have passed him by. A compound from a venomous reptile with no clinical history, isolated by a single researcher at a VA facility without major institutional backing, targeting a receptor that existing medications were already addressing through conventional chemistry. The development path was expensive. The source animal was obscure. Marketing a drug derived from Gila monster saliva to millions of diabetic patients was, from a pure optic standpoint, a significant commercial risk. Eng spent years trying to get the research taken seriously. He patented exendin-4 himself, independently, before any pharmaceutical company expressed meaningful interest. That patent, filed by one researcher protecting his own discovery because the industry wasn't moving, eventually became the foundation of a drug generating billions in annual revenue. Because exenatide didn't just work, it worked better than the existing standard of care in ways that reshaped the entire treatment landscape for type 2 diabetes. Reduced blood sugar, weight loss as a secondary effect, something no previous diabetes medication had done reliably. Reduced cardiovascular risk markers that synthetic compounds targeting the same receptor had failed to replicate. And then, researchers looked more carefully at the GLP-1 receptor pathway the Gila monster had accidentally eliminated and found something even larger waiting behind it. The entire drug class that followed, including semaglutide, now prescribed globally for both diabetes and obesity, traces its clinical lineage directly back to the moment John Eng looked at lizard venom and asked what it was actually doing. A venomous lizard that chews its victims unlocked one of the most commercially successful drug classes in pharmaceutical history. The lizard was always a pharmacy. It just took one really stubborn researcher to read the label.
Bee venom. The Roman surgeon and elder, Pliny, prescribed it for baldness in 14 BC. Named the dose, named the method, wrote it down.
That same compound from the same insect is now being injected into patients with multiple sclerosis, rheumatoid arthritis, and chronic inflammation in clinics operating under peer-reviewed protocols. 2,000 years apart, same animal, same poison, same result. Aotoxin, the venom in a single bee sting, contains a compound called melittin. Melittin shouldn't be therapeutic. It's a membrane-disrupting peptide. It punches holes in cells. That's the mechanism behind the pain, the swelling, the anaphylactic shock in allergic patients. It was never designed to heal anything. But at controlled doses, something different happens. Melittin triggers a cortisol response in the adrenal glands. Your body's own anti-inflammatory system fires up to counter the venom. The inflammation produced to fight the sting ends up suppressing the deeper chronic inflammation-driving conditions like arthritis and MS. The poison calls the cure into existence. Pliny documented this without knowing the mechanism. He observed that beekeepers rarely suffered from joint disease, that direct stings to arthritic joints produced relief. He was right about the outcome, just 2,000 years early on the explanation.
Here's what a bee sting actually does at the tissue level. Melittin hits the cell membrane like a battering ram. It binds to the phospholipid bilayer, the outer wall of every cell it contacts, and forces it open. Fluid rushes in, the cell swells, local tissue inflames hard and fast. In an allergic patient, that cascade goes systemic and can stop a heart. But in a joint space already destroyed by rheumatoid arthritis, where the immune system has been attacking cartilage for years, misfiring chronically, eating the body from the inside, that same violent inflammatory signal does something unexpected. It resets the misfiring. The adrenal glands flood the system with cortisol. Inflammatory cytokines locked in a destructive loop get interrupted. Patients report reduced swelling, reduced stiffness, and in documented cases, reduced pain that pharmaceutical anti-inflammatories hadn't touched in years. For MS patients, the effect runs deeper. MS destroys myelin, the protective sheath around nerve fibers. When myelin degrades, nerve signals misfire, movement fails, sensation distorts. Apotoxin, in controlled therapeutic doses, has shown the ability to suppress the autoimmune response targeting myelin. The nerve sheath doesn't regenerate, but the attack on it slows. In animal models, it stops. That is what Pliny's beekeepers were experiencing when their joints stopped aching. Not folklore, not placebo, an adrenal response triggered by venom, interrupting inflammation their bodies couldn't switch off on their own.
The method is called apitherapy. Live bee stings delivered to specific anatomical points, between 1 and 80 stings per session, depending on the condition being treated. 80 live stings, controlled, mapped, documented in peer-reviewed literature. It should sound extreme. It does sound extreme. It also works often enough that researchers across South Korea, China, and the United States have spent 3 decades trying to understand exactly why. This case doesn't have a clean verdict. It has something rarer, a dosage problem. Apitoxin works inside an extremely narrow window. Below it, no therapeutic effect. Above it, anaphylactic shock, organ failure, death. The margin between medicine and poison here is not wide. It never was. Several patients in apitherapy trials have died, not from the disease being treated, from the venom meant to treat it. Most drugs that kill at high doses are still safe to prescribe because the gap between therapeutic and lethal is engineered to be wide. Apitoxin's gap is not wide. And unlike every other case in this video, that gap has never been fully closed. Evolution spent 45 million years engineering bee venom as a defense mechanism, a chemical weapon for a quarter-inch insect to stop creatures 10,000 times its size. Apitherapy exists because Roman naturalists watched beekeepers age without arthritis, wrote it down, and someone 2,000 years later decided that was worth testing in a lab. The bee never changed. The poison never changed. Only our understanding of what a weapon can be used for did.
Viper venom? Romans didn't just fear it. They loved it. They ground the snake, flesh, fat, and all into a paste and fed it to their emperor every morning. Marcus Aurelius took it daily for years. His physician Galen formulated it, refined it, and staked his entire medical reputation on it. They called it theriac. They believed it was the most powerful medicine in the known world. For 19 centuries, virtually every physician in Europe agreed with them. Modern cardiologists just proved they weren't entirely wrong. Viper venom is a hemotoxin.
Its entire biological purpose is to break down blood, dissolving clots, destroying vessel walls, liquefying tissue from the inside so the snake's digestive enzymes can finish the job. It is one of the more efficient ways nature has developed to shut down a circulatory system, which is exactly why it became the foundation of modern blood pressure medicine. The venom contains peptides that block ACE, that's angiotensin-converting enzyme, that controls how hard your heart works to push blood through your vessels. Block that enzyme, blood pressure drops. The viper evolved that mechanism to stop prey from running. Pharmacologists isolated it, synthesized it, and turned it into the ACE inhibitor drug class, now taken by hundreds of millions of people worldwide for hypertension and heart failure.
Galen didn't know about ACE. He knew the viper's flesh produced effects he couldn't explain any other way. He was working with the right material, just missing the mechanism. Here's what viper venom actually does to a human body, and why that same process became the blueprint for saving one. A hemotoxic viper bite doesn't kill instantly. It dismantles. The venom enters the bloodstream and targets fibrinogen, the protein your blood uses to clot. It breaks the clotting cascade apart systematically. Wounds stop closing. Internal vessels begin leaking. Tissue around the bite site turns black as cells die without blood supply. In severe envenomations, organs begin hemorrhaging from the inside. The patient doesn't bleed out from one wound. They bleed out from everywhere simultaneously. That destructive specificity is what made viper venom scientifically interesting. Something that precise, something that could identify and disable one specific protein in the entire complexity of human blood chemistry had to be working through a targeted mechanism. And targeted mechanisms in pharmacology are valuable. When researchers isolated the peptides responsible for viper venom's blood pressure effects in the 1940s and 50s, what they found was a molecule that fit the ACE enzyme like a key fits a lock. It didn't damage randomly. It bound to one specific site and switched one specific process off. Blood vessels relaxed, pressure dropped. The cardiovascular system, straining against constricted vessels, suddenly had room.
The first ACE inhibitor, captopril, was synthesized directly from the venom peptides of the Brazilian pit viper, Bothrops jararaca, in 1975. It became one of the most prescribed drugs in medical history. The Romans were rubbing the source material on wounds and feeding it to emperors 1,500 years before anyone understood why it was having any effect at all. Here's where this case turns uncomfortable. Theriac, the viper flesh paste Galen formulated for Marcus Aurelius, contained up to 64 ingredients. Viper flesh was the anchor. Everything else was secondary. And for nearly 2,000 years, physicians across the Roman Empire, the Islamic world, and medieval Europe manufactured it, prescribed it, and charged extraordinary prices for it. Medicine's first blockbuster drug. Also largely unregulated, inconsistently formulated, and administered to patients who had no way of knowing what dose of active venom compound they were actually receiving. Some got better, some didn't. The physicians got paid either way. What makes this the moral case isn't that Romans used viper venom. The underlying pharmacology, as it turns out, was sound. What makes it the moral case is that Theriac became a commercial product before it was understood. Apothecaries in Venice held public ceremonies to manufacture it. Cities competed over whose formulation was superior. It was theater dressed as medicine, with a genuinely active ingredient buried inside that nobody could isolate, standardize, or dose accurately.
Toad venom. Not extracted, not synthesized. Roman physicians pressed the living animal against open wounds and waited. Yes, waited. They documented what happened next with enough clinical precision that a peer-reviewed paper published in the journal Chest in 1992 confirmed their observations were pharmacologically accurate. The toad's skin secretions act as a diuretic, they strengthen cardiac contractions, they reduce fluid accumulation around a failing heart. Pliny wrote that down in the 1st century. A cardiology journal verified it 19 centuries later. The toad didn't change. The disease didn't change. Only the equipment used to confirm what Roman physicians already knew did. Buffo, the common European toad. Widespread across the Mediterranean, slow-moving, easy to catch, never exotic, never rare. The animal sitting in every Roman field, every garden, every ditch bordering a military camp. Its skin produces bufadienolines, compounds that are at the molecular level structurally almost identical to digitalis, the compound derived from the foxglove plant that became the foundation of modern cardiac medicine in the 18th century. Both do the same thing. Inhibit the sodium-potassium pump inside cardiac muscle cells, forcing the heart to contract harder and more efficiently with each beat. That is the mechanism behind every modern digoxin prescription given to congestive heart failure patients today.
The 1992 paper in Chest didn't discover this effect. It confirmed that what Roman physicians had been observing and recording for centuries had a precise, identifiable molecular mechanism behind it. They were right. They had just been holding a toad instead of a prescription pad. Here's the problem with bufadienolides at full dose. The sodium-potassium pump they inhibit doesn't just exist in failing hearts. It exists in every cardiac muscle cell in every human chest. In a patient with congestive heart failure, where the heart is contracting weakly, inefficiently, inhibiting that pump slightly forces stronger contractions. The heart catches up, the fluid clears, the patient improves. In a healthy heart, the same inhibition doesn't strengthen anything, it destabilizes. The cardiac rhythm, which depends on precise sodium and potassium exchange to maintain its timing, begins to break down. Arrhythmia sets in. The heartbeat becomes erratic, then chaotic. In sufficient doses, it stops. This is not theoretical. Toad venom poisoning produces a clinical picture Roman physicians would have recognized immediately and been completely unable to reverse. Nausea, visual disturbances, bradycardia, then cardiac arrest. The margin between the dose that steadies a failing heart and the dose that stops a healthy one is narrow enough that modern cardiologists, using synthesized digoxin, the pharmaceutical descendant of the same mechanism, still consider it one of the most difficult drugs in clinical medicine to dose correctly. Toxicity is common. Monitoring is mandatory. The therapeutic window has barely widened in 2,000 years. Roman physicians were navigating that window with a live toad and empirical observation. The ones who got it right saved lives. The ones who got it wrong didn't get a second patient. But here's the part that should bother you more than it probably does.
The 1992 Chest paper wasn't written because someone went looking for Roman toad medicine. It was written because a researcher reviewing ancient texts noticed that the clinical outcomes Pliny described, reduced fluid retention, strengthened heartbeat, stabilized cardiac patients, matched the known effects of digitalis in foxgloves closely enough to warrant investigation. Nobody had checked before. Not seriously, not with modern tools. Pliny's natural history had been sitting in academic libraries for centuries, translated, indexed, cited. Classicists read it, historians of medicine referenced it. Nobody ran the compounds. When someone finally did, the bufadienolides in bufo skin secretions mapped directly onto the digitalis mechanism with enough precision that the paper's authors concluded Roman physicians identified a cardiotonic compound class that Western medicine didn't fully isolate until the 18th century. A 1700-year gap. Not because the knowledge was lost, not because the texts were hidden or destroyed. The texts were available. The toad was available. The patients with failing hearts were available. The gap existed because nobody considered it worth testing whether a Roman naturalist pressing a common toad against a dying soldier's chest might have been doing something that actually worked.
Deathstalker scorpion. Romans didn't just document it, they consumed it. Ground scorpion flesh was a listed ingredient in theriac, the imperial antidote taken daily by Marcus Aurelius as insurance against assassination by poison. That decision was not superstition, it was pattern recognition. Roman physicians had observed that scorpion stings, survived, seemed to confer resistance to subsequent envenomation. They didn't know why, they built it into the formula anyway. 2,000 years later, a researcher working with venom from Lyrus quinquistriatus, the most venomous scorpion on Earth, isolated a peptide that doesn't just interact with human tissue, it finds cancer, specifically, selectively, and it illuminates it. During brain tumor surgery, chlorotoxin, derived directly from deathstalker venom, binds exclusively to glioma cells and ignores healthy tissue entirely. Surgeons operating under fluorescence imaging can see exactly where the tumor ends and where the brain begins. That boundary in glioblastoma surgery is the difference between removing the cancer and removing the patient's ability to speak, move, or think. The scorpion the Romans ground into paste for their emperor was carrying a precision surgical tool in its tail. They just didn't have the imaging equipment to use it. Chlorotoxin is a 36 amino acid peptide. When chlorotoxin is attached to a fluorescent dye and introduced before surgery, it migrates to the tumor site and binds to every glioma cell it encounters. Under fluorescence imaging in the operating theater, the tumor lights up, not approximately, not at a rough outline, at the cellular boundary. The surgeon can see, in real time, exactly where to cut and exactly where to stop. Glioblastoma has a median survival of 15 months from diagnosis. One of the primary reasons outcomes remain that poor is the difficulty of achieving clean surgical margins in tissue where tumor and brain are visually indistinguishable to the naked eye. Chlorotoxin doesn't cure glioblastoma, but it gives the surgeon information they previously didn't have at the moment it matters most. The Deathstalker evolved that peptide to paralyze insects. It targets chloride channels in invertebrate nerve tissue with the same precision it targets MMP2 in human tumors, because precise molecular targeting is what this compound does, regardless of what it's targeting. Evolution built a lock-and-key molecule. Roman medicine and modern science found a different lock it fits.
But here's what Deathstalker venom does to a human body when Deathstalker's venom, chlorotoxin, arrives without a surgical team waiting to use it. The thing to note here is this venom is not a single compound. It is a cocktail. Chlorotoxin alongside agitoxin, cilitoxin, and charybdotoxin, each targeting a different ion channel in the nervous system simultaneously. Agitoxin blocks potassium channels in cardiac muscle. The heart's electrical rhythm begins to fail. Cilitoxin hits the same channels in smooth muscle lining blood vessels. They contract violently. Blood pressure spikes. Charybdotoxin disrupts calcium signaling across multiple tissue types at once. The result is a systemic neurological assault, convulsions, respiratory paralysis, cardiac arrhythmia. In children whose body weight gives the venom less volume to distribute through, untreated envenomation can be fatal within hours. The Deathstalker is responsible for the majority of serious scorpion envenomations across North Africa and the Middle East. It is not a rare animal in a controlled environment. It lives in the same desert regions where Roman legions campaigned for centuries. Roman soldiers were surviving Deathstalker stings regularly, and the physicians observing those survivals were the same ones deciding what went into Theriac. They watched men survive. They noted what changed afterward. They built that observation into the most important medicine in the Roman world. They were doing translational research. They just called it something else. Now here's where this case escalates. Chlorotoxin didn't stay in the brain tumor theater.
The underlying mechanism, a peptide that binds selectively to overexpressed surface proteins on malignant cells and ignores healthy tissue, is not specific to glioma. Researchers testing chlorotoxin against other cancer cell lines found binding activity in medulloblastoma, prostate cancer, colorectal cancer, and small cell lung cancer. Every tumor that overexpresses MMP2 or related chloride channel proteins is a potential target. That is not a narrow category. That is a significant percentage of the cancers currently killing people in oncology wards worldwide. The clinical application furthest along is tumor paint, chlorotoxin conjugated to a fluorescent molecule designed for intraoperative imaging. It entered human clinical trials and produced results precise enough to generate serious pharmaceutical investment. But the pipeline behind it is broader. Chlorotoxin is now being investigated as a delivery vehicle, a molecular homing system that carries chemotherapy drugs directly to tumor cells, releases them on contact, and leaves surrounding healthy tissue untouched. That would solve one of oncology's most persistent problems. Chemotherapy's damage to healthy tissue is not a side effect of treatment failure. It is a side effect of delivery imprecision. The drug cannot tell the difference between a cancer cell and a hair follicle, a gut lining cell, a bone marrow cell. Chlorotoxin, conjugated to the right payload, potentially can. The Romans included scorpion flesh in Theriac because they observed something in envenomated and recovered patients they couldn't fully explain. What they had inadvertently identified was a compound class with molecular targeting properties that the most sophisticated drug delivery research in the world is still trying to fully exploit. The Deathstalker scorpion has been carrying a precision oncology platform in its tail for 3 million years. We found the surgical application first. The rest is still being mapped.
Centipede venom. Pliny, a 1st-century Roman physician elder, documented the bite of Scolopendra, the giant centipede, in the 1st century with enough clinical precision that modern toxicologists reading his descriptions can identify the venom type quickly. The burning, the localized tissue destruction, the systemic pain radiating far beyond the bite site, refusing to respond to anything in the Roman physician's kit. He documented it because his soldiers were being bitten in the field, and because nothing he had stopped the pain. 2,000 years later, a research team studying Scolopendra subspinipes mutilans, the Chinese red-headed centipede, isolated a peptide from its venom called SSM6A. In animal models, SSM6A outperformed morphine as a painkiller by a significant margin. No respiratory depression, the mechanism by which opioid overdose kills. No measurable tolerance buildup over repeated doses. No signs of the addiction pathway that has made opioid-based pain management one of the most catastrophic pharmaceutical crises in modern history. Pliny couldn't stop the pain of a centipede bite with anything in his arsenal. Yet the centipede's own venom contained the answer he was looking for.
Most painkillers work by targeting opioid receptors, the same receptors that respond to morphine, oxycodone, and heroin. Effective because the opioid receptor system is the brain's primary pain suppression pathway. Catastrophic because that same pathway controls breathing, reward signaling, and physical dependence. Block pain through opioid receptors and you also slow respiration, trigger euphoria, and begin building tolerance that demands escalating doses.
SSM6A doesn't touch opioid receptors. It works through an entirely different channel, ASIC3, which sits in peripheral sensory neurons and transmits inflammatory and acidic pain signals to the brain. Block ASIC3 and a specific category of pain, the deep, persistent, inflammatory pain associated with injury, arthritis, and post-surgical recovery, gets interrupted before it reaches the brain at all. No opioid receptor activation, no respiratory depression, no euphoria, no tolerance buildup. The centipede evolved SSM6A to cause pain through one mechanism. Researchers found it blocks a completely different pain mechanism in humans, one that the entire opioid drug class was never precisely targeting in the first place. The centipede wasn't carrying a painkiller. It was carrying a key to a lock that opioids were never designed to fit. Here's what a scolopendra bite actually does, and why Roman physicians documenting it were encountering something their entire pharmacopoeia was genuinely unprepared to treat. The centipede doesn't inject venom through a stinger. It uses forcipules, modified front legs that curve forward, pierce skin simultaneously from 2 points, and deliver venom through a channel in each tip. The bite is fast. The pain is immediate and extraordinary. Burning, crushing, radiating from the bite site through the surrounding limb within minutes.
What follows is not simple local inflammation. Phospholipase A2 enzymes immediately begin destroying cell membranes at the bite site, tissue necrosis in severe cases, swelling, heat, and severe pain that persists for days. It's common to experience nausea, headache, cardiac palpitations, and there have even been documented cases of acute kidney injury from the venom's cytotoxic load overwhelming renal filtration. The pain is the clinically distinctive feature. It doesn't respond well to standard analgesics. Opioids provide incomplete relief because scolopendra venom pain is driven substantially through the ASI3 pathway, the exact channel SSM6A blocks, rather than through the central pain pathways opioids target. Which means Pliny's physicians, treating soldiers with centipede bites in the field, were applying everything they had to a pain syndrome that was physiologically resistant to everything they had. Not because their medicine was primitive, because the pain mechanism they were treating was one that modern opioid pharmacology 2,000 years later still doesn't address precisely. The soldiers Pliny was treating suffered through it. The venom causing their suffering contained the compound that would have stopped it. That compound sat undiscovered in the centipede's forcipules for 2,000 years while the opioid crisis killed 500,000 people in the United States alone. Over 500,000 opioid overdose deaths in the United States since 1999. That number is not a side effect of medicine working poorly. It is a side effect of medicine using the only precise tool it had for a problem that tool was never perfectly designed to solve.
The centipede has been carrying this compound for hundreds of millions of years. We have been in an opioid crisis for 25. The timing of the discovery is either very late or just in time, depending on how the trials resolve. The answer was in the animal causing the wound. It took 2 millennia, 500,000 deaths, and a research team studying Chinese centipede venom to find it. The centipede didn't change. The pain didn't change. What changed was that someone finally thought to ask what the animal doing the hurting was carrying inside it, and whether that was worth more than the bite. But here's the part that's genuinely unsettling. Every case in this video follows the same pattern. Romans find an animal. Romans observe what its poison does to a human body. Romans build that observation into their medicine. Modern science spends decades, sometimes centuries, confirming they were right. We tell that story as a story about ancient wisdom, about how remarkable it is that people with no microscopes, no mass spectrometers, no randomized controlled trials arrived at pharmacologically defensible conclusions through observation alone.
That is not the unsettling part. The unsettling part is the question it forces about right now. Every compound in this video spent years, decades, centuries sitting in an animal that humans interacted with constantly, dismissed as dangerous and never thought to look inside. Cantharidin sat in a beetle. Bufadinolids sat in a toad in a ditch. Chlorotoxin sat in a scorpion's tail. SSM6A sat in the forcipules of an animal we still treat as a pest. We didn't find these compounds because we went looking for them systematically. We found them because individual researchers working on specific problems happened to look at a specific animal at a specific moment and asked a question nobody had thought to ask before.
That is not a system. That is luck dressed up as science. There are roughly 1 million identified animal species on Earth. Fewer than 1% have been meaningfully screened for bioactive compounds. The biochemical library sitting inside the other 99% in venom glands, skin secretions, saliva, defensive compounds evolved over hundreds of millions of years of biological arms races are almost entirely unmapped. We are not at the end of this story. We're not even close.
The Romans knew that beetle, that toad, that scorpion, that centipede. They pressed them against wounds and fed them to emperors and wrote down what happened with enough precision that we are still confirming their observations 2,000 years later. What they didn't have was the equipment to find out why. We have the equipment now. We are using it on less than 1% of the available material. The next morphine is probably in an animal someone is stepping on right now. The next ACE inhibitor. The next compound that makes glioblastoma visible under a surgeon's light. The next non-addictive painkiller for 100 million chronic pain patients. It is sitting in a venom gland, in a skin secretion, in the saliva of something with too many legs that lives under a rock in a country where the healthcare system can't afford to study it.
The Romans didn't have the tools to find it. We do. We're just not looking. Having come this far, it's important we mention that these animals are not your pets. You do not want to keep them as around your home or kids as pets. In this channel, we look into bizarre animal facts, ancient human history, and natural science, uncovering the discoveries hiding inside the things we've always taken for granted. Subscribe to keep learning, and we'll see you in the next one.